recording. I just can't find the console of this thing itself. Okay, it's hiding. Now it shows. There we go. Okay, so we are recording. The screen is correct, and we can now get started. Cool. All right, so we'll start today's lecture with a homework. Okay, a new homework assignment, just so that you guys have something to work on in order to sharpen your skills with understanding the toy processor. I still call it the toy processor because that's basically what it is. It's just a little toy processor. All right, so this is the right class. All right, so when you go to the current module, which is assembly language programming, you get your first actual programming, well, okay, not first actual, but the first one using assembly language, which is division. Okay, so you click on division, and it tells you, what you can use, what is the input, what is the output, and so on. So your input is really stored in two registers. Register A has the dividend. This is the number being divided. And then register B has the divisor. Both of those are 8-bit wide, unsigned. Okay, signed division is actually harder than unsigned division. You may assume the divisor is non-zero, so you don't have to check for zero divisor. I guarantee that when I test your program, your divisor is non-zero, which also means it's going to have a value that will range from 1 to 255 because your register is 8-bit wide. The dividend, on the other hand, can be any value, can be 0 all the way to 255. So your program has to work for this entire range of values. Is that okay so far about the input? Real good? Okay, excellent. So the expected output is really quite simple. I just need the register A to have the remainder of the division, and register C to have the quotient of the division. Now, needless to say, because the dividend and the divisor are both unsigned, so the remainder and also the quotients are also unsigned 8-bit. Is that okay so far? Any questions at this point? Okay. So I also want a single halt instruction. Oh, instructor. Okay, typo. Okay, single halt instruction at the very end, so that when your execution reaches the end of the whole thing, it will stop at the halt instruction. And if you need to, you can also utilize additional RAM locations for variables if you need it. Okay, I don't know whether you need it or not. Okay, it depends on your algorithm and how you do it. If you do need additional RAM locations, you're allowed to use that. Efficiency is not used for grading. In other words, instead of using the actual fastest way of division, you can use successive subtraction. Okay, just like an elementary schooler. Okay, I give you 16, and I say, okay, what is 16 divided by 5? You go like, well, 16 is greater than or equal to 5. 16 minus 5 is 11. 11 minus 5 is 6. 6 minus 5 is 1. Okay, now we can stop. I have subtracted 5 3 times until we get to a number that is less than the divisor. As a result, the quotient is 3 and the remainder is 1. You can use that technique. Okay, that's okay. So remember, efficiency is not what I'm looking for. I just need your program to work correctly. Okay. Now, on the other hand, if you want to use the bit shifting, tricky stuff to do this, that's fine too. Okay. So it's entirely up to you to decide what algorithm you want to use for the division. Is that okay? So I think the easiest way to do it, which is successive subtraction, is reasonable. I don't think it's too difficult, for this class to convert into assembly code. So I think that's probably a good route to start. So my suggested route is like this. Okay, for those of you who say, I have a better way to do it. Okay, fine. You can do it your own way. Okay, this is just the way that I would do it. I would do it in C first. Okay, I would just do it in plain GCC. Okay, you guys all have access to code blocks, which is good enough. So I would do it in plain C, but I would also use standard int.h, as a header file, so that I can use uint_t as a type whenever it is applicable. In other words, I want to make sure that whatever logic I use will work with 8-bit unsigned numbers in the registers. Okay, so this way, I'm not going to write a program where, okay, if I have 16 or 32-bit registers, it's going to work, but if the registers are only 8-bit wide, it's not going to work. So you might want to make sure that when you write a C code, you also place the same constraints on your variables so that you won't be surprised later on when you convert that code into assembly. So I would do this part in structured C code just like your other classes. It's not going to be complicated, okay? I'm anticipating a single loop, okay, with no nested structure of any kind. It's just a single loop that can do this. Once your loop works, okay, once you double check your C code is working, then I want you to quote unquote flatten it. Flattening means we are removing the curly braces. We are removing the structure of the code so that you're converting a while into a conditional branch with a go to a label to other places. When the C code is flattened to the point where each conditional statement only involves one single comparison and a go to, then it is ready to be converted into assembly code. Because that's what your assembly code can do, a compare followed by a conditional branch instruction. So we're still doing okay so far with the homework assignment, the suggested route. Okay, so the suggested route is kind of a combination of a little bit of scenic stuff and a little bit of actual highway driving. Okay, so it's gonna take you to the point where you understand the instructions, understand how the processor works, and how to debug your program in assembly, but not so difficult that it is undoable. Okay, you have 1 week to do this, and I think it's sufficient time. To turn in is easy. You just turn in that one single text file that is the source file. Extension is entirely up to you. Okay, remember I want the source file, not the RAM file. Okay, the source file would be the ones that has all the instructions like LDI, LDST, JMPI, and so on. So do we have any questions about this homework assignment? Okay, no questions? Yep, go ahead. It's due in a week, so you have approximately 10 minutes less than a week to turn it in.
It's cutting it close.
Yep. Well, I mean, if you work on this, right now, and have something reasonable for me to look at, like 2 days later on Thursday, I would say you're doing good progress. I would suspect some people in this class may be able to get it done before Thursday. Okay, if you already understand the instruction set well enough, it's just a matter of time to actually put in the work. Okay. Are there any questions about the homework assignment? Okay, well, I'll keep it up just so that if you have any questions, we can refer back to it. So I'm going to save this version with that typo fixed, and then we'll go ahead and continue with the rest of today's lecture. So there is a question of how do we study when the material is kind of like this. Okay, so that's the first question I would like to answer. To answer the question, I would go to the shared folder. Anything in the shared folder is actually shared. Okay, in other words, you can print this out, take it with you in the second exam. Okay, and remember, anything that's printed or handwritten prior to the test, you can bring it in. So that would include every document that is in the share folder, not just in the processor subfolder. I would start reading this. Okay, if you're talking about studying, the first thing I would do is to start with studying the manual of the assembler. In other words, you want to be able to understand at least some important sections of this one. Okay, do you guys have any questions? No? Okay. All right, so the syntax is important, okay, because you want to know how to use the syntax, but I have used the assembler enough in this class that I think most of you got a pretty good sense of how the syntax works in this case. But if you do have questions about the syntax of the assembly programming language, you can go ahead and ask me, okay? It's fairly easy. You also want to understand what each instruction does, okay? So even though when you're programming, and in practice, I'm not going to ask you, okay, how many bytes, is from here to here. You do want to understand that certain instructions only take 1 byte and other instructions will take 2 bytes. Okay, so that part is kind of important. You also want to know the effect of the instructions. The halt instruction is just an infinite loop. It does not proceed after that point. The no op instruction doesn't do a single thing. Now, you might ask, why do we have a no op instruction? I mean, because that's just kind of stupid, right? I mean, why do you have an instruction that doesn't do anything? Well, it's because it's free. Because no op has an opcode of 0, 0, 0 to be exact, okay? And the wrong location 0, 0, 0, okay, 3 zeros, corresponds to the fetch instruction or the fetch microcode slices. Well, if the instruction is fetching also has an opcode of 0, 0, it goes right back to 0, 0, and then it will try to fetch the next instruction and so on. So the no-op instruction is not really by design. I did not intentionally, put a no-op instruction here. It's just that, okay, it just comes free. Okay. Then we have the arithmetic operations, add, subtract, and, or, not, and right shift. The compare instruction is the kind of exception to the rule because it doesn't store the result. But otherwise, it is the same thing as an actual subtraction. Okay, I have a pretty strong suspicion that you will need to use a compare instruction in your homework assignment. Along with possibly an add instruction, possibly a subtract instruction as well, okay? And you definitely need a halt instruction at the end, okay? Okay, copy and type. The copy and type instructions are designed so that you can initialize or you can copy the content of one register to another register, or you can also work in RAM as well. So the first instruction, which is LDI, is a little bit mysterious because it is actually taking up 2 bytes. Okay, this instruction takes 2 bytes. The first byte is the actual opcode itself, and then the second one is I. Because when you look at the actual implementation of this one, it is more like this. Okay, so I'm going to put here, whatever I type here is going to be updated in the actual document on Google Drive. So this one is actually x equals 2. It's actually the same thing as that. In other words, the first byte specifies the operation, and the operation itself is going to read whatever the program counter is pointing to and read that from RAM, store it into register X, and then it will increment the program counter. So when you look at the actual opcodes, it's going to take up 2 bytes. I itself is the second byte. Okay, we'll take a look at this later. Okay, I think you will need LDI as well in your homework assignment because this is how you can initialize variables. There are other ways to initialize variables if you just want to initialize to 0. For instance, sub AA will initialize register A to 0 because you're subtracting A from A, which is guaranteed to be 0, and then you're storing it back to A. But that will change the flags. LDI instruction does not change the flags at all. So that is the nice thing about LDI. ST instruction is just like what it says here. It will dereference register Y, whatever Y is. It can be A, B, C, or D. And whatever location it points to in RAM will store the value in register X. And register X and register Y can be A, B, C, D each. So you can actually use register A for both if you need to. Load is the opposite. It will read from memory. It will read from RAM. Whatever Y, register Y is pointing to, it will go to that location, read the byte at that location, and then store that byte in register X. Is that okay? And then we have CPR, which is copy register. Copy register is really just copying register Y to register X, nothing else. And then we have the jump instructions. JMPX is seldom used anymore, okay, but it is still here because occasionally you might need to use it. Okay, when we get to calling and returning, some routines will need to use it. What it does is it just copies register X, whatever it is, okay, A, B, C, or D. It will copy that register to the program counter. That's all it does. okay? So it will change the path of execution unconditionally so that execution will continue at where register X is pointing to. This is something you cannot do in C or C++. Okay, in C and C++, you can dereference and control which memory location you're accessing, but you cannot go to an arbitrary location to continue execution. But in assembly, with this instruction, you have the freedom to do it, which is really kind of cool, because if you have a table of locations to jump to, okay, you can actually calculate the index to use, to utilize the table, and then you can do that jump. The next one is JMPI, and then with an I here. The first I, which is a part of the mnemonic, is immediate. It stands for immediate. This I is actually specifying where do you want to go to as a constant. So this instruction is actually this. So we can say, okay, I. Okay. So this one is actually saying PC equals to same thing as the other one. In other words, it consists of 2 bytes. The first byte is the actual 8-bit opcode of JMPI. The second byte is the location where you want to jump to. So if the second byte is 06 in hexadecimal, then the program will continue execution at location 06. Is that okay so far with this? All right, okay. So the other ones are kind of the same thing, except they're conditional. Like JCX is conditional. It depends on whether the carry flag is a 1 or a 1 or a 0. If the carry flag is a 1, we use the register, whatever X is, A, B, C, or D, to update the program counter. Otherwise, we use the program counter to update itself, which means we're not changing where it is supposed to go, which is just continuation. JCI is a little bit different. JCI looks like this, but in reality, it is actually this. It is actually PC equals to, and then C question mark, and then we have PC plus plus colon plus plus PC here. Now, why do we have the plus plus PC as pre-increment as opposed to the PC plus plus, which is which is pre-increment for PP plus plus PC as opposed to PC plus plus, which is post-increment? What do you think?
If it's false, it'll move to the next operation rather than.
It has to skip that byte. Okay. So let me see if I can illustrate this as a. I'm trying to think of what tool I want to use to illustrate it. Okay, I think a spreadsheet may work here. So I'm going to use another spreadsheet here. And I can put it into the share folder later on, but right now I'm not going to label it. So the instruction is going to be a JCI. We'll specify location. Let's say 08. Okay. So the first thing we want to do is to figure out what kind of byte is generated for this particular instruction. And this will be tested in the exam, okay? In other words, I'm not going to give you an assembly program with 200 lines and have you guys to do the assembly, but I might give you a few instructions, such as this, so that I can assess whether you know how to assemble a program or not. Okay, so I can give you simple stuff to assemble. So in this case, we have to look up the instruction table, which is a part of the share folder. So we are looking up the opcode table here. The opcode table, which is also duplicated in the assembler itself, is really just a table. It's intended for human reading. It's not intended for machines. So when you look up JCI, which is row 17, it tells you the opcode is 01000100, which is 44 in hexadecimal. So we know for sure right now that it is going to be 44. Okay, so 44 is the first byte. And then the second byte is basically whatever we have, which is 08. Now these are all in hexadecimal, so I'm going to use quotes here just so that I can put a leading 0 in front of the 8. So it's going to take up these 2 bytes. Are we doing okay so far with this? So I'm going to show you 2 execution paths. One is showing you the execution path when the carry flag is a 0, and the other one to show you the execution path when the carry is a 1. When the the first one, when not PC, but when the microcode pointer is 0, 0, 0, okay, so I can do here, ucode PTR is 0, 0, 0. It will first read the first byte here, okay. It will read this byte, okay, and I have to combine that with PC equals to whatever that location is, okay. So let's assume this is a location L1, okay. So L1 is just a label. So if PC has L1 and the microcode pointer is 0, 0, 0, the first thing it's going to do is to read 4, 4 into the instruction register. So that's the first thing it will do, is the instruction register gets the value of 4, 4 in hexadecimal. That's the first thing it's going to do. Then in the second slice of the microcode portion, so when microcode PTR equals 0, 0, 1, two things are going to happen. The first thing that's going to happen is the microcode pointer will now become 440, okay? And then the second thing that's going to happen is the program counter becomes L1 plus 1. That's the program counter's auto-incrementing feature causing that to happen. Okay, all right? So far, it has no dependency on the carry flag at all. So at the next point, microcode pointer is now 440, and at that point, it is going to evaluate the carry bit out of the flags register. The output of the flags register contains the carry bit, and then it will look at that. If the carry bit, okay, which one do you want to examine first? When it's a 0 or when it is a 1?
0.
When it's 0, okay, so when it's 0. Okay, so we'll make the assumption, so we have to do a branch here. When it is 0, okay, C equals to 0 at this point. When it is 0, I should say equals, okay, there we go. Because we are not changing it to 0, we are just saying that it is 0. It is asserted to be 0. So when that is the case, are we branching? We are not branching, right? But what is the program counter pointing to? The program counter currently has a value of L1 plus 1, okay? Which means if I don't do a single thing, the next instruction is going to be the 08, which is wrong, because 08 is a part of the current instruction. If I'm not going to location 08 because the carry flag is cleared, I have to move the program counter past L1 plus 1, okay? So that is why we have to increment the program counter one more time, okay? So that's why in this case, we're doing a PC plus plus, or I should say PC equals plus plus PC, which is redundant, okay? But if I want to use the ternary operator, this is what we need to do. So this way, the effect is PC will now be, okay, I should use equals here. PC is now PC plus L1 plus 2, which is this location here, which is the next instruction, which is correct. So that when we go to the second slice of this microcode, which is 2 followed by all zeros, that's going to reset the microcode pointer register. Then it goes back to 0 and we'll do another fetch cycle. But then it would be fetching from column D, which is representing the instruction right after the conditional branch. Is that part okay? Okay. If there are any questions, now is a good time to ask.
I have one. It's only kind of related.
No, go ahead.
If you're using the ternary operator, you can't just say PC plus plus or plus plus PC?
You can't do a, actually, in that case, you have to say, you're right. Okay, so you have to say PC plus 1. Then you don't have to use an increment operator.
Well, I'm saying you can't use one? I didn't know that. I've never tried, I guess.
You can use plus plus PC, but in this case, I think it is better just to say PC plus 1 here. Oh. And this one doesn't need to be PC plus plus because you're changing it anyway. So whether you're incrementing doesn't really matter. So this would be a better way to represent it. The other one is actually a PC++. This one is a real PC++. Because this one does not change the execution path. So you have to kind of keep going. Whereas this one changes the program, the execution path right away. So whether you do a plus here or not does not really matter. Because this assignment is going to change the program counter anyway. So even if you have a PC++ here, it doesn't really matter. So I'm going to change the notation to this one, which is actually equivalent to the other one, but this is a better way to represent it. Okay. So do we have any questions at this point? What happens when the carry is a 0? Okay, so I'm just going to go through the simulation here. We go, my new code PTR is now at 441, and that's going to reset the microcode pointer. So the microcode pointer will reset itself back to 0. Then we are ready to fetch whatever instruction is next to the conditional branch. Do we have any questions about this particular simulation? You can do all this with the simulator as well. Okay, so all you have to do is to write a single instruction, which is the JCI08 instruction, and force the flags register to have a carry of 1 or a carry of 0. You can do that by just changing that one bit of that register, and then see what it's going to do. And you will see this sequence of events when the carry flag is a 0. What if the carry flag is a 1? Okay, so this is where I get a little bit lazy. Just do a copy and paste and use a new sheet over here. So in this case, we're going to say, okay, this part here is going to be changed because the carry flag is a 1 in this case. If the carry flag is a 1, then what will end up happening is the program counter is going to get whatever the program counter is pointing to, which means in this case, the program counter is going to get the value of hexadecimal 08. Okay, and then of course, the microcode pointer is going to auto increment to 441, and then right after that, it will reset itself to 0. But by the time the microcode pointer is back to 0, the program counter now has a value of 08, which means whatever is at location 08 is going to be executed next. So you have just altered the path of execution. Is that okay? Yes? No? Sort of? Okay. So we were just talking about how to study for this class at this point, because I'm not going to type a whole lot of notes anymore, because the whole design is already open sourced. So what we'll do is I'm going to show you how I would study at this point for this class. For the most part, it is going to involve using Logisim. Okay, and so we'll go ahead and start up Logisim first. And then we'll use the processor. Remember, the processor is one of the things you can bring to the test. Okay, if you want to make sure that you don't miss anything about the processor, print this out. Okay, print this out. You can zoom in, zoom out, print it on a bigger sheet of paper. I know some of you may have access to a larger printer. If not, you can always print it in sections. Okay, scale this thing, print it in sections, and then you can kind of stitch it together to be a larger piece of paper. Okay, that works too. So whatever you do, okay, you might want to bring this to the exam so that you have a reference to the design itself. So I'm just going to show you how to test the code that I was just talking about, which is also how you study for this class. So you go to the RAM location, okay, and I'm going to zoom in so that you can see what I'm doing. So you would go to the RAM location. 44 is the first byte. Oh, I forgot to reset the whole thing first. Let me reset it first. Okay. So you click reset first, and which will also reset the RAMs. Okay, the RAM locations. So this is 44, which is the opcode, and this is 08, which is representing where you want to go. Now, of course, we don't have any compare instruction before this, but we don't need to, because you have access to all the registers. You can doctor the registers to have whatever value you want it to have. So this is where we go back to the register, which is flags here. And you say, I want to change this flags register so that the carry bit is a 1. Okay? So then you ask, okay, but which one is the carry bit? The carry bit is bit 0. But how do we know that? You right-click into the ALU. You go to the flags output right here, and you can see bit 0 is coming from Cout. Now, if you're not convinced at this point that Cout is the correct one, you might want to double check that Cout is the output of this particular mux, and the input 0 of this mux and input 1 of this mux is B, and B is the borrow bit of the subtractor. So this way you know for sure that it is bit 0 of the flags register that you want to doctor if you want to test JCI. Are we doing okay so far? You're following this chain of reasoning. Okay or not okay? Okay? All right, cool. So then we go back to main, and now we know how to change the flags register. So if you want to test the program when the carry flag is a 0, leave it the way it is, okay? Because bit 0 currently is off, which is what you want, okay? So next is you want to clock it. When you clock it, this is where it is really kind of cumbersome for me because I have a smaller screen. This screen is only running at 1024 by 768, and I cannot run it in any higher resolution because you guys won't see anything if I zoom out. So it's going to be cumbersome for me because I have to kind of roll around to look at different portions of the design. So I type Control T, and one more time, and you can see how the instruction register is now having 44, which is the opcode itself. And if I do Control T one more time, the microcode pointer will become 440, which means we'll start to address location 440 in the ROM. Okay, Control T one more time. So this is the actual instruction. The way it works is we specify PC mux, which is this line here. It is 0, 0, 0. PC mux is used to control this multiplexer. So when PC mux is 0, 0, 0, what it's going to do is it will take input 0 so that it becomes the actual output. It connects input 0 to the output of the mux. Input 0 is corresponding to the 0 input is corresponding to bit 0 of flags, the register, and that turns out to be our carry flag. Okay? So it's using the carry flag to become PC mux because whatever the output is PC mux. It is also becoming PC enc here, so PC enc and PC mux are now both zeros. Okay, so now we go to the other part of the design and look at how these are actually utilized by the program counter. PCEN is coming out of the ROM, okay, so the microcode actually specifies it's time to update the program counter. But how are we updating the program counter? We are updating the program counter using this input, but this input is the output of a multiplexer. PC mux, which is now 0, is now selecting input 0 to be used to update the program counter. Input 0 is this wire. It's coming out of the adder, but the adder is not always adding 1 because the adder, the other input is a 0, 0, okay, and this input is just a program counter itself. So it all depends on carry in, whether carry in is a 0 or a 1. Carry in is not always a 1. Sometimes it is 0, which means the program counter stays put, okay? But in this case, it doesn't stay put because it is the OR between the address mux, which is currently turned on, and the PC increment bit from the ROM. So at this point, it is no, excuse me. PC enc is also a part of the circuit that we just talked about, but right now it is a 0. A 0 or 1 is still a 1, and that's why we are still incrementing. It is because address mux is a 1. Is that okay so far? Okay. So that means if I single clock at this point, the PC will increment from 0, 1 to 0, 2. Is that making any sense? Okay. and therefore it is doing exactly what we saw in the spreadsheet. Is that okay so far? Okay. So this is the first part. The second part is, what if the carry is a 1? So once again, we clear the entire thing, and the program is simple enough that I can just type it in 44 and then 08. But this time I also want to change the flag register to 01, because 01 means the carry bit is now a 1. Okay? And I think I remember to click the reset, right? Yeah, I did. Okay. So now we run the program again. Control T, Control T. The microcode pointer is about to change to 440, just like last time. I think I forgot to do one thing. Nope, it's not working. Okay, reset simulation. Let's do it one more time. 44 and 08. There we go. So we'll Control T, Control T. The instruction register is correct. Okay. Then we go to location 440. So we're back to the other point, but we also have to change the flags register. We can still change it now. It's not too late. So we change the flags register to 01 at this point. And you can also see PC mux is the same as last time. It is still 000, which means we are still using input 0 to become the output of this particular mux. But this time, PC mux becomes a 1, and PC inc is also a 1. So we go back to the program counter and see how this is all affecting how the program counter is going to be updated. The program counter is enabled, which means it's ready to be updated. How it is updated depends on this particular multiplexer. This multiplexer now has a 1 specifying the which input we should select. So instead of using the auto increment, it is now choosing the other path. But the other path is going through another multiplexer where this thing is controlling which input it is using. This input is basically selecting between a output of the register bank as opposed to the data bus of RAM. Okay. If it chooses this route, this is connected to the register bank, the output of one of the registers of the register bank. This route is connecting to the data bus. Is that okay? And when you look at the data bus, it's connected to RAM, but the RAM is already selected. It is also selected in the previous case. It's just that in the previous case, we don't really use the RAM to update the program counter, but in this case, we do. The load pin is a 1, which means we're reading from RAM, which also means whatever the address bus is specifying, the data bus is representing the content, which is 08 in this case. So this 08 is going all the way back to this input of the mux, which is fed into the other mux, which is now fed into the program counter. And as a result, when I have a rising edge, the program counter will now be updated to 08. It doesn't use the incrementing mechanism anymore. Instead, it's reading from RAM. This is how you study. It is not the same thing as studying for many of your other classes where you just kind of read something. With this one, you just kind of plug in an instruction that you say, okay, I want to understand exactly what happens when this instruction executes, and then you plug it in, and then you observe, what components of the processor is enabled, how the multiplexers are changing. Then you say, oh, okay, now we can see that path going from here to here to here to here, and that's how the instruction executes. So are we doing okay so far with the explanation of the JCI instruction and why it takes 2 bytes? The first one is just the opcode, going to location 440. The second byte specifies the location of where you want to go. So are we good on that so far? Okay. All right. So getting back to the homework assignment, are there any questions about the homework assignment at this point? Like, how do we get started with the homework assignment and how do we do it?
What do we do with the remainder?
The remainder is in register A. So we use register A to store the remainder. There's a reason why I use register A, which is also the register to store the dividend, because if you use a successive subtraction,
Yeah.
it's natural to have it there.
Okay.
I'm trying to make your job easier.
Yeah.
Register C has the quotient, because it has to be a different register for the quotient itself. It cannot be the same register as the dividend or the divisor. So the divisor has to be on its own. You cannot use that register for anything else. All right. So do we know how to, do you guys have a rough idea of how to get started with this one? Okay, all right, cool. So now we go back to the whole instruction set, and let me see if you guys have any questions about that. So the opcode table is a good, quick, easy summary of, what we do with this particular processor. And I just have to kind of do one thing here. I forgot. So this is +1, +1. Because if I don't do the +1, it's going to execute the next byte, which is the location that we are branching to, as if it is an opcode, which is incorrect. So that's why it has to be a +1. Yep.
I did have one question. Using the LDI, you assign values in the registry bank? Reg bank?
Yes.
Okay.
So the LDI instruction is described here. Let me zoom in just a little bit here. So the LDI instruction is this one here. You can see how that works. It is just going, because by the time we get to this part, the program counter is already pointing past the opcode itself. So the next byte, the byte after the opcode, is the content that you're copying to the register, and that's what this is saying. But we also want to increment the pointer, the program counter itself in this case, so that when we are back to location 000 in the microcode engine, it will start to fetch the next instruction instead of treating the constant that we're putting into the register as the next opcode.
And if you want to create labels, do we use an LD or something like that?
Yes, you want to use labels because labels can definitely help you
Should we
keep
assign
track
them,
of.
Should we assign them as with values?
Assign them as.
When we want to jump to them, we want to know where exactly they are. So
Yeah.
do we have to assign like values to them, or?
No, they would be labels. All right, so with this class, I think last time, did I tell you about the ungraded homework assignment, which is to find the absolute value of a register? Yes? No? I didn't say that? Okay. So I might not have mentioned here. So let's go ahead and use that as an example. Okay. So I'm going to use mousepad here to do this assignment. Okay, so the idea is find the absolute value of register A, store it in register B. Okay, this is my assignment. How do you do this? Okay, do you guys remember what is the absolute value? Okay, the absolute value is
The positive version of onside.
The distance from 0 of a number.
is the distance from 0 to that number. Yep, exactly. The direction does not matter. Okay. So the typical way to do this in assembly code or in C code, okay, so I want you to write it in C code first, is if A is less than 0, okay, then you do one thing, otherwise you do another thing. If A is less than 0, we want B to be the negation of A, arithmetic negation, and then in the other case, B is just A itself because we want B to be the absolute value of A. Is that okay? So now we look at this code and go like, okay, how do we do this? Well, the good thing is, this is already pretty close. So I'm going to use comments here, okay, because eventually I want to copy and paste this code into the assembler, because if I were using VI, I can do it with one single command, but it's okay. All right, so to compare A to 0, you have to put that 0 into another register in order to compare. Okay, so you have to do a CMP. So we know that we need a CMP instruction. We need another register to contain the value of 0. Now, there are several ways to do it. You can use the LDI B with a 0. That works. You can also, at this point, okay, it's a little bit tricky, but you can also use sub BB. which is subtracting b from b, which is guaranteed to be a 0, and then store it back into b. So that works as well. In a way, it is more efficient because it only uses 1 byte as opposed to 2 bytes, and it doesn't need to access RAM. Accessing RAM can be very slow because the modern processors can perform calculations in the ALUs a lot faster than you can read from RAM. So from that perspective, this is better, but it also changes the flags. Okay, so if you have already set the carry flags and whatnot flags that you need to use later on, you don't want to do this in between because it will mess up the flags. On the other hand, at the beginning of this program where the flags are not important, we can just do this part. So now the question is, which way do we want to compare? Well, we want to establish that a is less than 0, but it really can be less than 0 or less than or equal to 0. So now it depends on, which way you want to do the jump. So this is our else label, and we want to perform a single conditional branch j something I to else, okay? Because I don't want to save, instructions. So the question now is, okay, what do we want to do here? Well, you don't really have a choice, right? JLI is the only one you can use because we are dealing with signed numbers. Does it make sense that we are using signed numbers when you're dealing with the absolute value?
Once you wouldn't need it.
Exactly. Otherwise, if the number is unsigned, then you don't need absolute value. The number itself is always its own absolute value. Okay, so if I want a JLI to go to else, that means what I'm really comparing is 0 versus a. I want to go to else when 0 is less than a, which means a is non-negative. In fact, it is positive, not even 0. So we want to flip the order of the compare. When b, which is guaranteed to be 0, is less than a, we go to else, where we just store a into register b. Is that okay? So it's a trick, okay? This is a little trick so that I don't have to use unconditional branch after a conditional branch. And then we can move on to here, and we have to say, okay, but how do we do this? Well, before we do anything else, I probably want to make sure that I jump to the end of the entire conditional statement, put it here, put a single halt instruction so that I can stop. Now we can kind of focus and say, okay, what do we do here to negate a? We do not have a single instruction to do arithmetic negation. But you can also kind of remember that there are 2 ways to do this. Okay, because you can express this as b equals to 0 minus a, and b is already 0, right? So that would be the easiest way to do it. Or you can also remember that b can also be expressed as bitwise not a plus 1. We can do that as well. Okay, but which one is easier? This one is easier because we have everything in place already. B is already 0. We just have to subtract a from it, and we are done. Does that make any sense? The other one, you can do it, but you have to load the 1 into register B, do the negation of A, and so it's a little bit longer. So I'm going to choose this option. All right. So, sorry.
So I was saying it will be sub BA.
Yep. So this is just sub BA. Pretty easy. And then we have the unconditional branch to the end of the whole thing. This one here is even easier. It's just a single CBR, BA. We're copying register A to register B. Okay, I think it is case sensitive, so I'm going to change all the registers back to lowercase. There we go. Okay, I think it looks good at this point. So do we have any questions about how I come up with the assembly code in this case? Yep. You first and then you. Okay.
Can you scroll up a little bit?
Sure.
Yeah, I was gonna ask for the what are the outputs? What are the possible things that the CMP can do? Because it says that like CMP is x minus y.
Mm-hmm.
So wouldn't that be 0 minus a? Oh, but then it would flip the sign of the a. Okay, never mind. I get it.
It is, yeah, because eventually we are asking, is 0 less than a? That's all. That's what the conditional branch is asking. If so, we branch to else.
I was just gonna ask, what would it look like if you didn't do the trick?
do the other one?
Yeah.
Okay, so we can do the other one. So I'm gonna do something here, okay? If pound if, okay, you guys know what pound if is? No? Yes? No? Really? This is really cool, okay? So pound if dev,
Okay.
tag is lazy. Do this. Pound else. Pound end if. So the pound is what we call a compiler directive. It is actually not a part of the C language itself per se. It is part of the CPP or the C preprocessor language. It depends on whether the macro tag is lazy is defined. If it is defined, it's going to compile the code between the if def and the else. If tag is lazy is not defined, it's going to use the code between the else and the end if. So it's really nice and useful in a way, because if you have alternative implementation of some code in your program that you want to turn in, you're not ready to give up one, but you want to test whether the other one works the same way or not, you can use a macro definition, which you can define in even code blocks to control how the code is generated. And this way you can switch between the versions really quickly and easily, and be able to retain the code. You can also keep one as optimized, and the other one is, it's easy to follow. So it gives you a lot of options. So in this case, we don't want the end if to be here. That would be too low. We want it to be actually here. So now we can express alternatives of this code. So the alternative of this code is to do LDI B with 1. Okay, so we have a 1 here. A is going to be negating itself, so we want to look up the instruction set and see how we can do this. I don't use not very often, so I have to look it up. Okay, so not is just not x. Okay, it stores the result back into itself. So we're just saying not A, like so, and then we have to add it to B. So we just say add BA, and that's it. That's the alternative. So the alternative is kind of clunky, kind of inconvenient, because you have to first change the value of B, and then you have to do a negation of A, bitwise not of A, and then you add that version of A to B, which is already a 1, and then so now B is the absolute value, as opposed to sub BA, which is just one single instruction. So these are the two alternative paths. I have not implemented conditional compiling in the assembler, so the pound if won't work. So I'm going to have to comment out the code that we don't want. Is that okay? So I'm going to comment out all this stuff because I have not really implemented conditional branching or conditional compilation. So we'll just stick with this one. Are we ready to test this code? Okay, so the process, so this is kind of what you should be doing as well when you work on the homework assignment, is to first make sure you understand the instructions. If you have a question of, but I don't understand what compare is going to do, okay, I'm just not sure what compare is going to do, how it affects the flags register, and how is it going to store the result back into B or not. If you have questions like that, then write a single program with that one single instruction. Put something into B, put something into A, and then single clock through that instruction, do a control T. It might sound very tedious, but it's not, okay? Because it only takes 4 control Ts to go to the actual microcode slides. And once you get there, it will only take about 3 control Ts to go through the entire instruction. So with a total of 7 control Ts, it will finish the execution of that instruction. But when you're doing it this way, you can also look at the processor and look into the ALU, look into the register bank, and understand exactly how it works. Is that okay? But once you understand the instructions and you go like, yeah, I know what sub is going to do, I know what compare is going to do, then we can just go ahead and do this. So you Control A, Control C, copy all, go to the assembler sheet. Okay, I haven't opened it today yet. So we go to the assembly sheet here. you go to the source tab. Okay, the source tab is right here. And if you already have code here, that's okay. You can always just, select the whole block and delete. But you don't want to do any type of, changing the columns or the rows. So you just want to do a Control V to paste. Make sure that you don't get any errors here. Okay. And if you don't get any errors here, you go to RAM file. You do a file, download as. CSV is fine. The other one, I think the last one will work as well. Just save the file, and this is absolute value. Then you switch back to the assembler, to the simulator. Reset simulation, which also automatically resets everything, including RAM. Now you right-click on the RAM, load image, go back to the location where you saved the file. In this case, I saved it in the temp folder. Okay, click open. Now we have the program here. Now, before you run the program, you might want to do a few things. Okay, it's almost free to you. It just takes a little bit of time to set it up. So in this particular program, I might want to keep track of the flags register for one thing. I might want to keep track of the two registers that I want to use here, which is register A and register B. So I go to the register bank and I say I want to keep track of register A, keep track of register B. I also might want to keep track of the program counter. In other words, did we branch or not? Okay, the program counter will tell you that. Okay, so if you have any other registers you want to track, the flags register is already here. The instruction register, I don't think is going to be very important, so I'm not going to track it. But whatever you want to track is fine. Even components inside the ALU, you can track. Okay, so all of these things, everything that is displayed here, you can track. It's not going to generate a very long list. It will only generate a row when something is changed. Okay, when something of interest is changed, then it will generate a row in the log. So if there's nothing happening to the stuff that you want to track, you don't get any rows. There's no log corresponding to those. Okay, so here's my logging. You can close the window. I'm just setting it up right now. So we can then go to simulate and have clock enabled, and it's all done already. Okay, you can tell it's done by looking at the program counter, and you can see that it is not changing anymore. It is now stuck. The instruction register is a 01. The program counter is now stuck at 09, which is the halt one byte, one instruction past the halt instruction. That's because location 000 in ROM auto increments the program counter. So that's why it's pointing to location 9 when the instruction is at location 8. Okay, so we'll stop the simulation, and then we can go back and take a look at the log. So we go to logging, we go to table, and you can see how the program changed the various parts. The flags register is changed. The one thing that got changed is the 0 flag, which makes sense because 0 minus 0 is 0. Because that's effectively what we're comparing. Because register A has a default value of 0, right? We load a 0 into register B. 0 minus 0 is 0. But we don't know which one it is because we have another. We have the sub BB instruction also to initialize register B. That would also set the register like that. But you can also tell which one we are executing. The program counter went from 0 to 1, 2, 3, 4, 5, 6, and then it jumps to 8, which is going around the else branch. So we were taking the then branch in this case. Does it make sense that we would take the then branch? Okay, let's look at the code again. Does it make sense that we would take the then branch but not the else branch? So the question is 0 less than 0? Okay, if 0 is not less than 0, then we are not going to take that JLI to else, right? Which means we will go through the then branch, update register B with A, which is, we would actually subtract A from B again, which doesn't do anything, and then we'll go to the halt instruction. Is that okay? Shall we test it with an actual negative value? See if it will flip the sign. Okay, let's do it. So at this point, I don't really have an easy way to reset the whole processor without disturbing the RAM. So if you don't like having to reload your program all the time, what you can do with your own design, okay, is to take out this reset here. So disconnect this line and use a push button specifically just for RAM. Okay, so you use your wiring, go get a button. Nope, it's not here. Go to input output, grab a button. There you go. Okay, there we go. So now I'm decoupling the RAM from the rest of the system. So now I can click reset of the processor. Oops. I can now click reset of the processor without changing the content of RAM. It's up to you. I mean, it's not a big deal. If you don't want to do this, that's cool. But we do want to change the registers because this time we want register A to contain a negative value. So we go to register A and go, well, let's put a negative value here. Do you guys want to use FF, which is -1? Okay, so FF goes here. Go back to the main part of the design. And now we can clock through the whole thing. Let's see, go to logging here. Can we clear all this stuff? I think it automatically clears and starts from the beginning every single time, so that's good. All right, so let's go ahead and run it. Stop right now. Go back to the logging. So you can see this time the logging is a little bit different. Oh, it didn't clear the other one. Dang, okay. I thought it would, but it didn't clear. So register B is, this is register A, and this is register B. So we know that it did the right thing because register B did end up with a value of 2. But we also want to look at the program counter, and this time you can see how it took the else branch and not the, no, this time it still took the then branch, because you can see how it went from 0 to 1, 2, 3, 4, 5, 6, and then it jumped to 8. It skipped over the 7. Okay. All right. So let's test it again. Okay. So we click reset again, and this time we want to change the register A to a positive number because 0 it will still go through the then branch. We want it to go to the else branch this time. So 0.5 is good because 0.5 is positive and it is non-zero. Okay. And then we go through the simulation again. The program is still the same. We go back to location 0. So we go simulation, text enabled. Okay, the whole thing is done. And then we look at the logging. And the last part of the logging, we end up with a 5 in register B. So that is correct. If you look at the program counter, it also shows you too. Because we go in from location 1, 0 to 1, 1 to 2, 2 to 3, and then 3 jump all the way to 7. So we skipped the then branch and went for the else branch this time. So is that okay? I mean, do you guys get a feeling of what tools are available to you to debug your program? Yes? Sort of? Okay. So my only advice is to get started early. Okay, because it takes time to get used to the tools themselves. Okay, to get used to the flow of the logic, you do some changes to the program, you copy and paste the code, you take the RAM file, you put it into the RAM, you run the program, and then you try to diagnose what the problem is. And I can tell you this is a lot easier than some of the programming that I have done before I took on this job. Okay, because you do have complete visibility of all the registers. You can keep a log of everything and whatnot. When I was in the industry, okay, if you guys think this is irrelevant, that's okay. I can stop talking about my past. Okay, but when I was in industry, we had to program these single board computers. By today's standard, they're really, really old technology. And these controllers are basically a single board computer with a processor, a RAM chip, a ROM chip, and stuff like that. Not very unsimilar to what we are seeing here, except it's physical. But there's no simulator. Okay, so what you do is you write the code, okay, in assembly. You assemble the program, put it into the ROM. Okay, so the ROM is actually replacing our RAM here. It also has its own RAM, but it has a ROM chip to run the actual instructions. If something goes wrong, you have no idea how it went wrong, because when you look at the single board computer from the outside, it doesn't show you anything. There's absolutely no visual cue of what just happened. Okay, most of these single board computers have 1 or 2 LEDs that are under the control of software. That's your only way of debugging the program. If I get to a certain point, turn on the LED. If I couldn't get there, then LED is not on. And on top of that, you have to use these these ROMs. Okay, let me show you what it looks like, because some of you, it's actually kind of relevant to some of you, but not the entire class. These are called EPROMs. Okay, which stands for erasable, programmable, read-only memory, which sounds like oxymoron, right? If it's read-only, how come it's erasable and programmable? So they look like this. Okay, this is a really typical chip that I used back in those days. It has a optical window, okay, which is clear, and you can program it using a high voltage. So you have to put it onto a special ROM programmer in order to change the content of these things. Once you program it, the program cannot be changed. It's read-only after that point. So you plug it in, physically plug it onto the board that you're trying to debug. And when your program doesn't work, then you have to use a screwdriver and very carefully pry it out of the socket. Because if you're not careful, you will bend the pins. If you bend the pins to the point where it cannot be repaired, then that chip has to be tossed away. They're not cheap. So you do this with maybe 10 of these things. So now you end up with 10 used EPROMs, right? And then you put it into a tray. You put it into it looks like a tiny little oven, but it's not. It's basically a UV eraser. They just turn on a UV fluorescent tube, and it takes about 15 minutes to erase these EPROMs. So after that, now you have 10 fresh EPROMs again to continue your debugging session. So by comparison, having this simulator is a lot easier to debug your programs already, because you can track things down. You can say, oh, show me how the registers are changing. I couldn't do that with single board computers. And on top of that, I was also using my own assembler at the time. So when the program doesn't work, you're not quite sure whether it's the program itself or the assembler or the single board computer. Because there's some hardware engineer, some electrical engineer is in charge of designing the circuit board, and sometimes they make mistakes. So they give you a circuit board that is not functional. So you're trying to figure out why it is not working. Is it my own code? Is it the tool? Or is it the actual hardware that is not working? By design, it cannot work. That was a fun job. I did that job for 8 years. So I learned a lot from that job. So any questions at this point? No questions? All right. We got 10 minutes left, okay? So I'm not gonna bug you with more stuff related to the homework assignment. Instead, I'm gonna give you some questions. I'm gonna show you programs, and then I'll ask you questions that I want you to think about. I will write about it, so don't worry, this stuff you will see notes about it. And it is about where do we store local variables, okay? And how do we deal with recursion? So we're gonna do a really simple program, and it has recursion. Okay, so here's f, which has a single variable. We call it n. Doesn't do a whole lot. If n equals to 0, we stop. Else we do the recursion, f n minus 1, and main doesn't do anything other than calling it. Let's do a 3. There we go. Okay. And just to make this more fun, just a little bit more, we have local variable x, and x equals to n. There we go. All right. So x is what we call a local variable. There are two types of local variables. When you refer to something as a local variable, you're only specifying the scope of the variable, which means, oh, okay, x can only be accessed inside the function f in this case. That's the scope. But the default of local variables is called auto, which means it is on the stack, it is on a per invocation basis, as opposed to static, which means there's one single thing, okay, regardless of your invocations, and it's always there. A static is always there, whereas an auto, it means, it is only allocated when you call the subroutine. Okay, so let's go ahead and compile this program. As you can see, this program doesn't do a single thing. It's recursive, but it doesn't do anything in the recursion itself.
Gives you a warning. X is not used.
It will give you a warning that x is initialized but not used. It has a value, but it is never used anywhere. Okay, so we'll save the file, gcc-g-o main, and then we'll do a warn all, main.c. Yep, there you go. And then we say gdb main, list the program, and we'll put a breakpoint in function f. This is really neat because you can just refer to the name of the function. Okay, so when we run the program, we'll also put a breakpoint in main too. So let's put a breakpoint in main, like that. Run the program. Now we are ready to call something. So my question now is, do we have any variables allocated at this point? Nothing. We have no variables, allocated at this point, because the only local variable is variable x, and the parameter is kind of like a local variable, except with the exception of when you're talking about a local variable like x in this case, the initialization is inside the function. The caller has no control over the initial value of a local variable. A parameter is just like a local variable, with the exception of its initial value is specified by the caller. That's the only difference. Okay, from the conceptual perspective, that's the only difference between a local variable as opposed to a parameter. Okay, so now we can single step. Okay, so single step will go into the subroutine that we're calling. This is the first invocation, and GDB is pretty nice. It tells you, oh, the parameter n is 3. With single step, you can say, oh, tell me what is x. X is 3. Cool. X n equals to 0 is false. So we go to f of n minus 1. Single step. We called it again. N is 2 now. Okay, cool. Single step. Print x. X is 2. Not really surprising, right? Single step. We go to the else branch again. We call this again. N equals 1. We print x. X is now 1. Single step again, we go to the else, n is now 0, single step, x is now 0 as well. Cool, nothing suspicious right now. But what about that x that was 1? What about that x that was 2, the x that was 3 to begin with? Where are they now? They're stored somewhere, but where are they? And what about, so how many levels have we called function f? And how do we keep track of all that stuff? Okay, so one thing you can do is bt, backtrace, in GDB. This is really cool, because it shows you how we got here. It shows that right now, #0 is the current, what we call frame, okay? It's the current invocation that is active right now. So frame 0 is always where we are. And at this point, we are at the 4th invocation of f, okay? Because you count n equals to 3 is the first one. This is now the 4th one, okay? And at this point, we are now at line 5. The other line 9s are the points where the recursion happens. So we got to this line 5 because somebody called f from line 9, from line 9 of f, from line 9 of f, from line 15 of main. So that's how we got here. Cool. What about the variable x? Okay, how do I know the variable x in frame number 2, for instance? Okay. Now in GDB, it gives you the option of changing your frame. If you don't say anything, you're automatically in frame 0. which makes sense, which is your current point of execution. But if you ever need to go back to a previous frame to see, oh, but what is variable x in that particular frame? Just say frame 2, and then you can say, tell me what is x. X is 2 in that case. Is that okay? Another thing I want you to kind of at least observe is the addresses of these variables. Okay, so I'm going to print the address of x. Okay, some gigantic number because it's a 64-bit architecture. Okay, we go to frame 1, and then we do the same thing. Tell me what is the address of x? Okay, not the same, which is good. Okay, because we don't want the same address to be corresponding to the x. Go back to yet another frame, frame 2. Print the variable x. Go back to frame 3, and look at variable x again. Do you see any regularity? Do you see a pattern here? The current frame or local variables of the current frame always has an address that is lower than those of the previous frames. It is always following that specific order as well. Okay? That is kind of interesting. I think that that's kind of interesting. So that means if the recursion keeps on going, then the local variable x will have a lower and then a lower and then lower and lower and lower addresses. And you can also clearly see in this case that we have multiple instances of variable x. There's one variable x per invocation as opposed to per function. Okay? When we say per function, we are saying per function definition. When we say per invocation, we are talking about actual dynamic behavior of the program that we can observe right now. Is that okay so far? Does this help explain, how recursion works for those of you who have exposure to recursion? Okay. So it makes you wonder, what else do we need to remember when you call a subroutine, right? What do you think is the other thing that is absolutely essential when you call a subroutine? Calling is easy, right? You identify the name of the subroutine and you just say, hey, continue execution over there. What happens when you get to the end of the execution of that subroutine? What do you do?
Having to go back.
I know we have to go back, but how do you know where to go back to?
Yeah.
What do you think?
Stack.
The stack, okay. So somebody has to say before the calling, before branching to the subroutine, somebody has to remember that first. It's like, oh, when that subroutine is done, this is where we need to go. And then leave a little breadcrumb somewhere, right? But in the case of recursion, it gets a little bit complicated because in Fortran, which is not capable of recursion, they have static areas per function to say that when this function is done, use this location to tell you where to go back to. That doesn't work with recursion because with recursion, every single point of recursion can be different. I just use a very simple example where it's recurring from the same place. But if you have something like Fibonacci, there are 2 points of recursion. So where do you return to? It depends on whether it's the first time we call Fibonacci from inside itself or the second time, right? So how do you keep track of all that information? So those are the questions I want you to kind of at least think about. I just planted a seed in your mind, okay? So depending on the soil condition, sunlight condition, and water condition of your mind, you might have a little bit of a, how do you call those things? Seedling, yeah. You might have a seedling by Thursday, and for certain people, they might get a dead seed on Thursday, but let's hope that's not the case. Okay, so on Thursday, we're going to build upon these concepts, okay? And I will show you schematically, okay, what is being done when we call a subroutine, and then we'll talk about how to do it in assembly code. Okay? Are there any questions? I don't think any one of you took cisp310 from me because I stopped teaching that class like 3 years ago. Did anyone take cisp310 from me? I don't recognize anyone. You did? Okay, you did. Okay, so you might want to go back to your notes for that class. Because I did talk about how calling and returning works. Remember the spreadsheet stuff, the really tedious stuff? That's what it was for. Is to prepare you for this class. So since the majority of you did not take that class from me, I'm going to talk about it from scratch. So you guys just have a slight advantage over the rest. You have potting soil instead of just regular soil. All right, so I'll see you guys over at the lab for those of you who want to get started with this homework assignment. And stop.